Hello, this is Mr. Gilmore with the 1.2 lesson on angles. Let's jump right into this. What is an angle? An angle is a pair of rays with a common endpoint. So we think about what a ray was. A ray is a point on a line and all the points chosen to one side of that line. Well, when we make two rays from the same endpoint, we've created then an angle. Now, instead of calling these two rays just rays, we're going to give them kind of some jargon for our angle. We're going to call them sides. So if I were to say, hey, what's the sides of these two angles? I really am referring to the two rays. Another thing to note is with that common endpoint, we want to give another kind of jargon name to that endpoint. We're going to call it a vertex. So if I say, what's the vertex of that angle? What I'm really asking is, what's that common endpoint that the two rays share? Down below, we have an example of an angle where G is that common endpoint in which we produce both rays from. And then point F and point H, point F is a point on one distinct ray and H is on another. So if I were to say, what are the two sides of this angle, G or the angle below, I could say the two rays are GF and GH are the two sides of that angle. And then also I have point G being the vertex of that angle. To name angles, we use all three letters to name an angle. Now, in order to name it, there is an order. Okay, there is a special order to these. We name these with the vertex in the middle. So I can give this angle two valid names. I could call it angle FGH, where I choose a point other than where the vertex is, and then I choose the vertex for the middle, and then lastly, moving to the other side of my angle. So a point on one side, the vertex, and then a point to the other, I have myself an angle name. So FGH, or I could call this angle HGF. As you see, the invalid names clearly are not correct because I do not have point G as the vertex in the middle. So the very center spot must be the vertex. There are other ways to name an angle. Here's an example of using just a single letter to name an angle. And in a lot of cases, we can use this single letter. We're going to talk about some of the dangers of using a single letter here in just a second. I can just call this simply angle G. Now, the reason why I can call this simply angle G is because I have precisely two rays coming out of endpoint G. But there's an issue with that. What if I were to throw in a third ray? If I were to say, hey, look at angle G, that's where we get into some ambiguity here. And because if I were to say, look at angle G, am I referring to, I don't know, this angle here? Am I referring to this angle here? Or am I referring to the entire angle? We want to be able to distinguish them, which is why when we have more than two rays coming out of a endpoint, we want to make sure we use the three-letter angle name. That's going to be more appropriate than just using the single letter. But in a lot of cases, we can get away with using the single letter. There's one other way we can name angles, and that is by tucking numbers into the mouths. And we'll see that that can be used quite often as well, where we just simply tuck a number into the angle mouth and call that angle by the number tucked in. Now, be careful. That number is not representing the measure of the angle. No, no, no. It's just representing the name of the angle. So I could call, instead of calling it angle RZS, I can say just angle 1. Or instead of calling it angle SZT, I can just call it angle 2. And so tucking numbers can be quite convenient, especially when you're dealing with many different angles. Tucking a number in makes it a lot easier to name instead of having to watch or kind of distinguish between all the different letters that we have tackling. And you'll see a combination of a lot of different versions of where we do three-letter names to the single letter name to the numbered name. So just keep in mind, there are many different ways we can name angles. Every angle has a measure. That's actually a pretty bold statement. We're going to talk about why every angle has a measure in the future. But in order to give an angle of a measure, we want to talk about the common unit we use in that angle measure. We use the common unit of degree. Imagine taking a full sweep, meaning we take a ray and we sweep it all the way around, completely around itself of its endpoint back to where it started. We make one full revolution around. We want to chop that entire revolution up into 360 little slices, little tiny bits of that revolution. If we were to take one of those slices, we call that a degree. So a degree is really 1 out of 360, right, of a full revolution, a complete revolution around the endpoint, which means that we can then take a ray and we can we can revolve it, not maybe the full rotation, but we can revolve it a certain way around our endpoint. And what that means is, then we can then take and measure what is the amount of those tiny little slices. How many slices did it take to get from one point to the other? That means, or from one ray to the other ray. What that means is we then have a measure to that angle. Here's a quick illustration of showing this, understanding how we take the revolution, one complete revolution, and dissect it up into 360 pieces. So if I were to take ray AB and rotate it around point A over to the ray AC. Think about the ray at the bottom kind of moving or rotating to coincide with the second ray, ray AC. The question is, how many of those little degree segments did we go, right? Those little degree slices did we go? And in this case, we have 120 of those. 120 it took to get all the way from rotating from AB over to AC. And that means we have a definition. We can define that angle to have a specific angle measure of 120 degrees. We use a little symbol, right? Forgot to mention that, the little symbol up in the upper right-hand corner of our number to denote the degree symbol. You will see that we'll use degrees quite often when we talk about the measure of our angles. Now, here's another question. Why did I rotate the direction I chose? Why did I go from AB and rotate counterclockwise toward the ray AC? I could have actually done both. I could have actually gone counterclockwise or clockwise to rotate my ray AB to ray AC. So which one? Which one will we choose? Are we going to choose the degree of going the 120 degrees or to 240 degrees back to the ray AC? We typically choose the smaller of the two. So whether we're rotating clockwise or counterclockwise, but that's not really what we're choosing. We're not really choosing clockwise or counterclockwise. We're choosing the smaller of the quantities is what we will typically stick with. So in our case, we would go with what's the measure of this angle is 120. Because really, when I produce two rays from the same endpoint, I really am creating two angles there with different measures. There is, of course, one angle that we can create where it really only has one measure, and we'll talk about that one in the future. So how do we actually denote what the measure of our angle is in a diagram? Symbolically, we use still that little degree measure symbol. But where we put that is we tuck that into the mouth of the angle, very much like how we name the angle with a number. We just tuck that into the mouth. This one does include the degree unit, so we want to make sure we put that symbol in there so that we know the difference of whether you're giving the angle a name or you're giving the angle the measure. Right. So in this case, we do have the measure of angle A is 28 degrees. To denote the measure of an angle, we use the little letter M that we tuck in front of the angle symbol. So we have this little angle symbol here in the middle, and then we put this M right in front of it saying the measure of. The measure of. Now here's a quick question for you. Is the measure of angle A equal to angle A? That is a definite no. You're comparing the measure, a quantity, a number, to the actual physical object, and we can't compare that. That's not nothing that we can actually compare. So if I were to compare measure to measure, we could do that. I can compare physical object to physical object, yes, but I can't actually compare a quantity to a physical object. So that's something we got to make sure we denote the difference of. That little m does matter, okay, when we say the measure of an angle or just simply the angle itself. We're going to find the use of hash marks again with our angles. If we take a look at our diagram below, we're going to find that in the diagram, we find that there are two angles here, angle BAC and angle DAC, that have single hash marks. And then we have another pair of angles, angle BAE and angle DAF, that have a double hash mark. It just simply denotes to our reader that, yes, we have equal pairs of angles here, right? BAC is definitely equal to this angle, and BAE is definitely equal to DAF, and we could denote that to the reader, right? Hash marks denote equality. But here's another question, and I've asked this in a previous lesson about our hash marks. See, I've already got two questions definitely answered. Those are definitely true. But what about if I were to compare angle EAB to angle BAC? So really what I'm comparing is I'm asking, are these two equal? Right? That's really more of a question. Are these two equal? That's a double hash mark and a single hash mark. If you said yes, then you're wrong. But if you said no, You're also wrong. See, this one is a cannot be determined. We simply don't know whether or not those two angles are equal or not. And a lot of you said, no, they can't be because one's a single hash mark, one's a double hash mark. Hash marks only say what they mean to say, which is they only denote which things are equal. They do not say that things are not equal. That's what not what that the hash marks do not have the power to do that. They only simply can do one thing, and that is show equality, not show inequality. Well, you may have another reason of saying, well, it's definitely no, because look at the mouth of EAB. Man, that mouth is much greater than the measure or the mouth of angle BAC. That BAB's got to have a bigger measure. Does it? Because if you said your reasoning behind that was because it looks that way, that is a wrong justification. We cannot simply base things off of what it looks like. What we can base things on is not by the what our eye perceives, but what the truth holds. So you got to be extra careful with that, right? So these two here, they honestly could be equal. We do not know. So our answer in this question is cannot be determined, CBD. All right, so just be careful with hash marks. We have angle bisectors. So if we were to produce an angle, just any sort of angle, you can actually place a point on its interior such that it splits the two subangles equally. So here down below we have point P on the interior of the mouth of angle ABC. Now when we produce the ray BP, right, with ray from the endpoint B through the point P, and we produce it such that it cuts the two subangles ABP and CBP equally, we can call this ray an angle bisector. So it does split our angle into two equal subangles. Now, this is a pretty bold statement that I'm going to make here in just a second, which is every angle has an angle bisector. Every angle has an angle bisector. That's a bold statement. We're going to talk about why that's true in a future lesson. I can't just say things are true and just will them to be true. No, I have to actually prove them to be true, explain that they are true. A couple other relationships we're going to encounter with angles to finish off this lesson. There are quite a bit of little definitions we're going to end up with in this lesson. We have what are called adjacent angles. Essentially, adjacent angles are angles in which they have a ray in common and their interiors do not overlap. So, for example, down below we have a pair of adjacent angles. We have angle BAC and angle CAD. Those two angles there are adjacent. Why? They share a common ray, so they have this ray here, AC, in common. And notice that where I highlighted the mouths of them, they don't overlap each other. We got to be careful with this definition. A lot of times we can make an easy mistake. For example, what if I were to say, look at angle BAC? We marked that one already, but look at angle BAD. You could argue, hey, don't they have a common ray? Yes, they do. They do have a common ray. They have a common side, but their interiors overlap, which means we don't satisfy the complete definition of adjacent. So I can't call those adjacent angles. The mouths of the angles cannot overlap. Those interiors must be separated. And so we're going to encounter a lot of adjacent angles. In fact, there's a relationship we're going to look at here in just a second in which we use the definition of adjacent within a new relationship of angles. Let's take a look at our next pair of angles. Let's call these vertical angles. Vertical angles, we're actually going to be seeing in next chapter. We use quite a bit vertical angles. What we describe vertical angles are two angles in which their sides form two lines. Two angles in which their sides form two lines. In other words, we can say that the only thing in common that these two angles have are the vertex. They only share that common endpoint between their two angles. So down below we have an example of a pair of vertical angles. I have angle ABC and angle DBE. Both of those are a pair of vertical angles. Why? Because look at the sides of the ray AB. Here's one side, here's the other side of this angle. And if I were to actually then highlight the sides of my second angle, DBE, notice that those two form two lines. So whenever I see two lines crossing, I know for certain that there are vertical angles that are formed there. What's interesting about vertical angles is when I form one pair, I really get a second pair out of the deal. I actually have a second pair of vertical angles in here, angle ABD and angle CBE. That's a second pair of vertical angles. We're going to be talking a lot about vertical angles again in the future. We'll see these come up. So be mindful that there are several new relationships you may not have heard of before, may not have seen before, that we'll encounter in this chapter some more and then in the next. Our last relationship we're looking at is what's called a linear pair or linear pairs. To define a linear pair, it really are there are two angles that form a linear pair, and when they form this linear pair, they have to have two things for them. There's two things in the definition. The first thing is they have to be adjacent, and we see that here in our lesson here, or in the slides, adjacent. And this is a big, right? We want to say, and there's a second thing that has to happen, and their non-common sides form a line. So that's the second thing that has to happen there in order for us to form a linear pair. You'll note that the diagram from the last slide and this slide didn't change. It's because in the same diagram, I can find pairs, actually many pairs of linear pairs. And so like one that we'll point out here on the left-hand side, or in the diagram here, and then on the right description, I have this angle here, ABD, and angle DBE. That is one pair of a linear pair, right? Those two angles form a linear pair. And why is that? Well, they're adjacent, right? They meet that criteria of being adjacent. They have an array in common, and their interiors don't overlap. And the second thing that we see is they're non-common, right? This is this highlighted ray is the common ray. So what are the non-common rays? It's the other two, right? Not being used. These two rays form a line. That's where we get a linear pair. And if we take a step back and kind of undo what we've got written in here and look at the diagram again, we can see, hey, there are more linear pairs in the same diagram. I've got this angle here, CBA, and angle ABD. Don't they form a linear pair? Yes, they do. They are adjacent, and their non-common sides form a line. And I can keep going. There's two other pairs in there, but just keep in mind that we'll encounter many linear pairs and also vertical angles. We're actually going to see a relationship between linear pairs and vertical angles here in the future. All right, with that, make sure you're working on the 1.2 worksheet, and be good and do good.